Hello. In this video, I'd like to talk about the spatial surfaces that are used in the L-range modeling family. Won't talk about quite all of them. There are some other surfaces in F-range, for example, that help it to model herbivore populations. But we will talk about essentially all the surfaces included in G-range and the base offering for L-range. And I'll use the G-range application and its surfaces to do so. There's a lot to say here. I won't be able to go into all the detail, or the video would be very long. It still may be a long video, but hopefully helpful. By the time we're done with the discussion, you should have a pretty good sense of the kinds of information that are used in these tools. We are talking of spatial surfaces, again, rastered layers that are used, so grid ASCII format. I can speak more about that if you'd like. But different ways of approaching this. One way would be to look at and to place ourselves where we are in these tools, and I'll do so here. And so here we have the structure of the model once installed. So if you download the original G-range application, and it includes that big collection of spatial data, then that's the layers that occur within G-range, the main application folder, and then within that, the layers folder. So we've got the parameters folder, storing parameters, of course, where the model produces output, and then we've got the layers folder. That folder then, I'll return to this interface, I believe, but for now I'm going to go to another tool, and that is ArcGIS. And so we'll review the surfaces here. So I've got a little zoom in here. Let me scroll down. I need to remember to keep it all current. Little zoom in so you can read the names here. That said, the names aren't necessarily critical. There may be a file or two that has to remain, but basically these names are customizable. You can change them as you wish. You can replace information in G-range. You need to create information for L-range. And so as people decide to update G-range, and I hope they do, the original application is a decade old now, you can replace these surfaces, put in better surfaces, more up-to-date information. Now, when you do so, you should take on the idea of assessing the application, making sure that it's still doing well enough to address the questions of interest to you. But that is certainly a doable thing. It's a good thing to consider. So as these surfaces, if you change the name, for example, they are pointed to by the simparm.grg file within the parms folder. So there's another video that addresses simparms.grg and describes its contents. Much of the file is a series of pointers pointing to these spatial data. And so, again, if you change the name of any of these files, you'd want it to be named appropriately in that parameter file as well. Well, I'll go through this list and I'll give you some sense of potential sources, but those are changing so rapidly, and people seem to be better at finding improved and more exotic sources of information than me. And so I won't go into great detail there, but I'll mention a few sources along the way. The first file is, actually the first two files, you'll see that I've modified one slightly, just a copy, is a land file. And again, you can see an extension on these surfaces is, or perhaps part of the main name, is 0P5. That's my shorthand for 0.5 or half-degree surfaces. So just part of the name I adopted. But here you see the land surface. This is land versus water. And as you might guess, it's not used directly in modeling. There's no information to be gained from this. Why I've got it here is so that G-range can use that surface to make the output more compelling, to allow people to place themselves on the landscape. If G-range, which simulates rangelands, if that's what people wish to do, If you have the rangelands only turned on and GRange produced that as a global output, it could be difficult to place yourself amongst the scattered landscapes that were simulated. And so this surface is used to give the simulated rangeland cells some context, some spatial context. I'll skip the next one and speak of zones. Zones is really simple. If you think of the structure of the file, all of these are grid ASCII files if you're familiar with that format. It's got the 6-line header and then a big square of numbers. For the zones, those numbers simply count up from 1. That's all it is. It's providing a unique identifier to each cell on the landscape. And so in the upper left, it starts at 1. And then the next cell over to the right is 2 and 3 and 4, etc. And then the next line is numbered all the way to the bottom right corner. And so you can see, to give you some sense of what I'm speaking of, I don't think I'll take the time, but if perhaps I can scroll down all the way to it's just off the screen there, but it's 259,200 pixels help to form the zone file. So again, this surface is providing a unique identifier to every landscape patch that's being simulated, and it's part of the bookkeeping that GRange and LRange do. The next surface is also, it's used in modeling directly, but it's generated. It's not something you typically go and download. We make this file. So the zone file, for example, is easily made with just a few lines of Python code and in many other ways as well. And then this is made with a GIS package typically as well. Pretty straightforward to make. I'll mention that in a moment. But this is latitudes. You can take it literally. So here, for example, we are speaking of GRange surfaces, and so we have values from negative 89.75 to 89.75. That is, the latitudes going from negative 90 to positive 90 for the globe, and then the center of each cell for this half-degree resolution grid is labeled. And so what that is doing, I can scroll up just a little bit or move up just a little bit. What that is doing then is providing latitudes to the model that are used to determine solar radiation and day length, primarily day length. So the model needs to know the length of each day for every landscape patch that's simulated, and this latitude is providing that information. Presumably some formula could be included that would replace this, but this is the most straightforward approach for me. And so latitudes are pretty easy to create. It sounds a little complex, but it's not. If you have some experience with the GIS, for example, it could be programmed, again, with a bit of Python code if you are speaking of geographic coordinates. But if you have your zones surface, this file that I spoke of, if that's available to you, then you can take that surface, convert it to points, a whole lot of them, in this case 250,000 points. And then there are tools in GIS that are, like in ArcGIS, it's called add XY. It's just a command, add XY. It adds the latitude and longitude to every point. And then you can take the longitudes and convert them back to a raster layer. I'm sorry, the latitudes, hope I spoke correctly. Take those latitudes and convert them back into a raster layer, and you end up with this surface. Well, before we continue, I'll mention one more. That's the elevation layer, which is actually an artifact. It's a holdover from earlier modeling. It's not used directly in modeling. It's still part of the package, and so included both in the inputs and in the spatial data collection, but not used directly in modeling. At some point during some update, it will go away, presumably. But it is, as you may guess, the digital elevation model for the world. Well, now I'm going to move back to the top and turn on another copy of the land and ocean surface that we spoke of. Except here I've made the land clear. Some of the surfaces we'll talk of next have black for the landscape, all of the ocean, and so it's a little difficult to place yourself. So here we have ocean and then whatever might peek through the openings. The next surface then is deciduous. This is the deciduous tree component. And so tree cover is provided to the model. It's a cover, so it's between 0 and 100 as a percent cover. And in this case, it's deciduous tree cover. And you end up being able to indicate the proportion of each cell that's occupied by deciduous trees, or the percentage perhaps of each cell occupied. And so you can see in the eastern U.S. there's a higher component of deciduous trees. The next surface, as you might guess, is evergreen trees. So this is the evergreen tree percent cover. So again, values from 0 to 100, and the proportion of each cell that's occupied by evergreen trees. These values are originally from, I don't recall it. Please do check Boone et al. 2018 for the original sources. But now I'd encourage and use in current applications Copernicus, for example. They've got, the European group have pretty extraordinary breakdowns of this kind of information, very useful in this regard. And so you see again high evergreen cover in the Amazon and in the Congo and such. The next is shrub cover. And so shrub cover is like it sounds. Here I didn't break it down by deciduous and evergreen. That information is rarely available. And in fact, in the original application for G-range, even shrub cover itself was difficult to come by. But again, more recent efforts have made that information more readily available. And so for the African application, for example, I've used a much better data set from Copernicus. Herbaceous cover is like it sounds. In this case, this is coming from this is the older data set coming from MODIS data and the vegetation continuous field data set. There are better sources now that I've used in Africa, for example, from the same source I've cited. And it is herbaceous cover. So again, from 0 to 100% herbaceous cover. And so you may wonder why there's no bare cover surface. That's determined through the simple math. So if you take, for example, deciduous cover, evergreen tree cover, so we have deciduous trees, evergreen trees, sum those up for tree cover, some as well the shrub cover and the herbaceous cover, you'll end up with a number. Subtract that number from 100, and whatever's left is bare cover. And so that's not provided as a spatial surface. The next surfaces are precipitation and temperature. And so we have average precipitation as a value that's, I need to check, but it's stored as the centimeters times 10, which brings us back to millimeters, I recognize. But this is a common practice in storing spatial data. The storage of decimal values is inefficient, and so many times we use a scaling factor to correct for those values. And so in this case, it's multiplied by 10, and then the software divides that by 10 to return it to its appropriate units. It's embarrassing how often I have to double check this, make sure it's right. I now incorporate both temperature and precipitation as outputs from the model. They're certainly used in modeling, but I also read them and write them, and that allows me to ensure that something's not off by a magnitude, for example, because I have the units incorrect. These data are, again, a long-term average. I tend not to update them during climate change experiments or the like. They're used in a pretty subtle way in the century model. These are not the climate data that are driving the model. I'll cite those separately. These are just long-term averages, but they could be updated in the context of a scenario. A similar story for temperature and average temperature. So this is the annual average temperature for all the areas in the world. And so there's no time component here. This is average annual and averaged over 30 years perhaps. So again, a very long-term pattern used in a few calculations within the biogeochemical processes incorporated from century into the L-range modeling family. We need a layer, I've cited this in other videos, a layer that connects to the landscape units file. This is one of the central bits of information in the modeling tool. And so the landscape units file, GRG, it's actually land_units, but again, you can change its name. It is stored within the params file folder, and it's storing all the parameters that describe how vegetation grows for different landscape units. This is the spatial file that provides those landscape units. So again, as you may see here from the Boone et al. 2018 paper, that was using biomes for the world, 15 biomes for the world, known as SAGE biomes. Please see the reference in that paper. And so it's labeled SAGE here. And if you count it up, there are 15 different biomes here. And so, again, you can go, there's a direct connection then between the red one, biome number 4 here, to the collection of parameters within the landunits.grg file that describe how vegetation should grow within that landscape unit. The next file is the land cover file. And so I've addressed this when speaking of the land cover legend parameter file. In the base application, it was called Goji because of a very detailed land cover classification done for the globe. It had almost 100 types in it. And so you see them here, all of the land cover types. This is not playing as heavy a role as the landscape units file. Instead, this is just allowing you to turn individual land cover types on and off in the model. So we have these big biomes, say. They can be whatever you want to use to classify landscape units. And you can turn on or off individual patches within those areas. So, for example, you may have a large landscape unit that is coniferous forest, say, and it includes urban areas that you want to turn off. It includes water that you want to turn off, big lakes or the like, and that you would do here. You'd go into the legend file in the params folder and set the leading value in each line that you want to turn off to 0. Turn the others on by putting in place ones, and then it will model the land cover types that you've indicated. The next set of data come from the World Harmonized Soils database. And so I happen to use in the most recent application, wasn't available when the original one was done. I used, in the original I used the Harmonized World Global, the Global Harmonized World Database, or whatever the name may be. Please do refer to the paper for a reference. There's now a regridded copy from Oak Ridge Lab, which I find helpful as well. And so they've gridded the data so it's easier to interpret and to produce output. Here you see layers that you might expect, that you might guess. So we have 6 layers, happen to fit on the screen, informing the model about soils. And there are 4 soil layers represented. That said, it's only informing, in terms of a spatial context, a topsoil and a subsoil. I've got them sorted alphabetically here, so you see subsoil is first. So you have a subsoil bulk density. I believe it was down to 30 centimeters. Have to check that. It's described in the Harmonized Soils database. So we have bulk density, which would be grams per square meter. There would be soil carbon, which would be a grams per meter in this context. Again, check out the, in my case, regridded Harmonized Soils database, and they'll have all the detail. Sand is percent, so again, it's just texture. We've got, pardon me, I've skipped some. We've got clay, gravel, sand, and silt. Each of those is a textural assignment, so a percent. And those are used to initialize G-range in many ways, following the century model. And then we have another 6 layers that are doing the same thing for the topsoil. And so you see again, bulk density, total soil carbon, the clay content, the gravel content, silt, and sand. And they look like this, or this, or that. Now, the last entry is a placeholder. I can almost fit it on the screen. The last entry is a placeholder. It is, in this particular case, as you know, as you may know, there are 3 kinds of primary information that drive the dynamics of the L-range modeling family. And this is common for many ecosystem models. That's precipitation, minimum temperature, and maximum temperature each month. So again, the time step for these tools is a month. So it's the precipitation in the month, minimum temperature, and maximum temperature. So here I have, for example, precipitation. It's named in a particular way. And some of it is adjustable. Some of it is programmatically determined and would require just some trivial editing to name it any way you wished. So here we have, for example, and there are many surfaces here, we have the precipitation. So you see I've started the name with P. For 2006, the year, it's for December. And again, I loaded the wrong resolution. I've got 1 degree data as well in the folder. And so you'll see that in a moment. But you can see that it's for December 2006. And this is the precipitation that in this case was reported from the CREW database. But there are many sources now for lengthy histories of climate data and projections as well. So the idea then, the P, for example, is adjustable. I'm not sure you'd want to, but as you wish. There are pointers in the simparms.grg file that describe the beginning of this file's name. So it says P. That is how these things are named, and gives the folder where they're stored. And then it gives a suffix, so I should have said prefix. Then it gives a suffix as well, which is, in this case, 0.5, or here it's 1.0, unfortunately, that tell the model what the rest of the name will be. And then the model creates the middle part, because that's changing every month. It uses the date and the month, so the year and the month, to generate a name. And so it can locate the file knowing that those names are in a predictable format. And so really the shorthand is, if you're putting in climate data, so G-Range comes with a whole set of climate data, use that directly. If you're putting in your own, you can format it to match this, and things should work fine. If they don't, it's a pretty trivial change to the software. I won't talk about that here. This video is getting long enough. But it's just a bit of a change to change the format to match the naming structure that you've adopted. So let me move back to the other window, and then we have the climate data. So again, we've got crew data. We have crew is a source out of the UK. And you can see this is observed data that extends through 2006. And again, you can see precipitation. So 2005, 2004. I happen to store 2 resolutions in this folder, but you typically have 1 resolution unless you've downloaded GRange itself. And it is precipitation data times 10. So it's not storing decimal points, it's storing integers times 10. That's what allows it. So storing centimeters times 10, bringing it back to millimeters. And then the software is going to divide by 10 to bring it back to centimeters. Same thing for maximum temperature. Here I've adopted X to indicate a maximum temperature. Again, you could change that if you wished in the SimParm file. You could change that designation, but X is the maximum temperature. You can see at the top of this list, you have 1901 as the year, January, and a resolution I happen to adopt. And the minimum temperature, indicated with an N. The logic is all the same. You provide a prefix and a suffix, and then the software creates the middle part of the name so that it's able to load those images month after month and do the processes that it needs. Again, if you're just using GRange directly, this should happen automatically, but if you're making any changes, then you'd want to make sure everything's behaving reasonably and reassess the tool so that you know it's adequate to address the questions you have at hand. Now I'll mention the other spatial data are for fire and for fertilization, where you can schedule fires at a given time, a given month, or a given year, and a given year. I've talked about that in the video on simparms.grg. And then the others are global circulation collections. So they're from global circulation models from different groups. So here we have Hadley and IPS. I believe that's Hadley. And so we have here, it's the representative concentration pathway 4.5 and 8.5. So here you see precipitation, maximum and minimum temperatures. And so and they store the same kind of data in the same format. So if we go to maximum, you see the years and the X as a prefix and the suffix and such. And so if I'm doing a climate change scenario analysis, for example, I can go into the SimParm folder, put in a pointer to, as part of the prefix of the simulation, put in a pointer to my baseline climate data and run a scenario or more as you wish to represent variability. Then I can go into the SimParm file and change that to point to climate data. I may change it to point to HDG underscore RCP 4.5, and then it would load that climate data instead of the other and be representing a climate future scenario. So here, for example, I trust it would continue to 2070 is where I stopped, for example. Well, a lot of information, I realize, and more can be said, but hopefully that gives you a sense of the kinds of spatial data that are used in the L-range modeling family.